Looks like we're live. Hello everyone and welcome to yet another recreational programming session. How about that? How about that? But you didn't expect that shit to happen. Hello, welcome. Let's make a little bit of an announcement and officially start the stream. So, let's do a little bit of a ping. First of all, not really live, a red circle. Live on Twitch. Right, so, and what are we doing today on Twitch? I just realized that I forgot to bring the dashboard from Twitch. God damn it. Okay, so what we're doing today is basically we are implementing Brainf compiler, actually native Brainf compiler. Right, trying to be like a family friend in here. Native, and I'm gonna give the link to twitch.tv/Tsoding, and I'm gonna ping everyone who interested in being pinged. And I just realized that I probably also didn't update my title. God damn it. Yeah, I recently got sick, so that's probably why I just like being very unorganized right now, so I'm really sorry about that. Yeah. So we're going to be implementing the Porth, we're going to be implementing the Brainf compiler in Porth. Right, so this is going to be very interesting. So it's going to be very, very interesting. Yeah, I do feel better, Mustafa. Thank you so much. Yeah. I do feel better, otherwise I wouldn't try to stream. I didn't want to stream today at the beginning of the day, but at the end of the day I just kind of started to feel a little bit better, so I feel I can try to stream, so should be fine. Did you get flu or something? I think I got flu, but this could be a COVID as well. COVID is basically a flu of 2022, am I right? So flu is such a like 2019 meme, am I right? Who gets flu in 2022? Like COVID. You get straight up COVID. So implementing native brain. I'm pretty sure Twitch is not gonna be okay with me putting word fuck in the title. So let's actually put fuck just in case. Right, implementing native Brainf compiler. Well, like, I don't know, like, people put things like shit in the title, right? So if shit is okay, is fuck okay as well? I don't really know, so I'm not just gonna risk it for the biscuit. So, who knows? Even though this stream is marked as, like, for mature audience, my audience is immature. I'm joking, you guys are very mature. So Pzemo version 2, thank you so much for Twitch Prime, thank you, and welcome to Epic Port Club. Port. So, yeah. Okay, so there is this meme floating around of people implementing their own language and then implementing an interpreter, a brainfuck interpreter in their language, right? So it's among the people who watch my series, right? A lot of people who watch my series, they also implement their own languages, and one of the things they do is they just implement a brainfuck interpreter, which is actually a pretty cool exercise. And I also wanted to do that as well, but since it's such a widespread meme, I thought that would be kind of boring, right? So everybody's implementing brainfuck interpreter, so let's try to do something more interesting. Let's try to implement a brainfuck compiler, right? So let's implement, compiler that takes the brainfuck code and generates assembly code. But not that, we already have a backend for a compiler. We have a Porth backend. Let's use a Porth backend to implement a brainfuck compiler. So essentially, let's write a program that reuses the backend of Porth, generate Porth intermediate representation, and runs it through the generator of Porth to generate the assembly. So I think that will be actually kind of interesting. So, and that's literally what we're gonna do today, right? So we're gonna try to implement Brainfuck compiler using the Porth backend. So, and see how it goes. And I would say that Porth intermediate representation is actually quite compatible with Brainfuck, right? So it's relatively easy. What we'll need to do, we need to pre-allocate like a big you know, chunk of memory for the tape, then we can keep the head of the brainfuck. The head of the brainfuck maybe on the top of the stack. Maybe we'll be using only like one frame of the stack of porth. And yeah, so we're gonna just like translate all of the brainfuck commands into like sequences of the porth commands. And that should theoretically work. So I don't know, we'll see. Though I'm not 100% sure about the loops though. So the loops are gonna be kind of tricky, I think. They could be kind of tricky. But we can probably try to work that around. So yeah. So let me see if anyone else subscribed. All right. Okay, let's go ahead and just like do that and see how we can do that. Well, I'm gonna fetch the latest version of the compiler, right? Because I developed compiler like off screen. And let's go. I'm gonna merge origin master. Right. So how are we gonna call this thing? I'm gonna call it brain.porth, I guess. It's a brain porth. Right, it's a brain porth. Let's include std.porth and also, you know, introduce an entry point where we're gonna say hello world, right? So we're gonna do puts, and that is basically it. And then I'm gonna try to, let me actually rebootstrap the compiler just in case, right? So I fetch the latest stuff, right? Oh, by the way, I dramatically decreased the size of the assembly recently by removing redundant labels. Now the assembly looks like this. Right, so there's no like redundant, you know, labels or anything like that. So it's just like became like very, very compact, which is nice. So it's under 1 megabyte. Very, very cool, especially for the, you know, for Git. Okay, so I'm gonna go to README and I'm gonna try to find FOSM. Right, so I'm gonna run FOSM. And by the way, reducing the size of the assembly also increases the speed of the FOSM compilation, which is also nice, right? So it comes with a benefit, I think. Right, so we're compiling the compiler. And now we should be able to have latest compiler, and we can keep recompiling the compiler with itself. Isn't that beautiful? Isn't that beautiful? I think it's pretty cool. So can the compiler compile itself under one? Yeah, it still compiles itself under 1 second. This is actually pretty cool. I really like that. The compiler recompiles itself in under 1 second, being completely unoptimized, by the way. Completely unoptimized. When porth Tetris? Sounds like a good idea, thank you. I'll probably implement it at some point. I don't want to implement like any more games in porth until I have graphics. God damn it, I'm already spoiling. So yeah, we're gonna have graphics soon, so but I'm not gonna spoil too much. But yeah. All right, so let me see. So this is going to be brain porth, and let me do something like brain porth, right? And if I try to run this entire thing, right? So it says hello world. You can't turn on assembly comments. You can turn on assembly comments, but I didn't create an option for that yet. Right, so if you need to debug, you still would be able to turn on the comments, right, in the future, but not right now. All right, so I suppose I can try to basically straight up include some of the parts of the compiler. So, right, in the compiler we have different like parts. We have the compiler itself, we have the code generator, and we also have optimizer, right? So I don't think I'm gonna include the optimizer, but I'm definitely gonna include the compiler itself, right? I'm pretty sure I don't need the Lexa though. I think Lexa is not needed, right? So, and I also want to include the generator. So check is a type checker, right? So we also don't really need a type checker. I think we don't need it, at least for now. Maybe it would be needed for like checking the like balanced brackets, but you can check that like outside of the type checker. You can create your own type checker for that. So I don't think it's that big of a problem. All right, so if I just like include these two things, is it going to work? Because some of these things, they do depend on some other things, so it may require including more stuff. By the way, this is actually quite good exercise of like knowing how decoupled the entire compiler is, because I want the parts of the compiler to be reusable by third-party programs, right? So for example, I want the lexer to be reusable by third-party programs and stuff like that. Furthermore, I'm thinking that some of the compiler definitions should be reusable by the user programs. So for instance, I think some of the definitions like, let me actually show you, src com intrinsic, like all of these definitions, I think they should be part of the standard library, right? So the user programs know the IDs of intrinsics and opcodes. Right, and the compiler and the program use sort of the same definitions. The reason why they may want to know that is because we may introduce some interesting constructions like quote, right? Quote, and this is going to be some sort of a block, right? So quote is going to be, you know, a keyword, and this forms a block into which you can write your own code, right? So your own code if, and like you can just put some code in there, and what it will turn this entire block into, right? So you may even assign a name to this block. It will turn it into a memory block, basically a sequence of OP instructions of the compiler. So this sequence of OP instructions is available to your user program, so you can interpret it or do something with it. So you can basically quote the code. Right, and this could be useful for the compiler as well if the compiler wants to insert certain port code into some sort of things, right? But I don't want to like do that on a level of OP instructions, like OP codes. I want to do that, like I want to say, okay, I want the compiler to include this piece of port code in front of each function, right? So, and then I can say that, okay, so the code that I want to insert is going to look like this, and yeah, so I hope this makes sense. Lambda functions, this is not lambda functions. I'm not talking about lambda functions. The closest thing I'm talking about is maybe macros, but even what I'm talking about is not macros per se. It's more of a reusing the same intermediate representation for the user programs. Okay, so let's continue. Okay, I'm gonna try to compile this entire thing, right, and see. So we have count types, and count types is not like available at compile time, I suppose, right? So we'll probably have to include types in here, right? Types.porth. All right, so tokens. Ah, god damn it. Okay, so the types want to have also tokens, so all of that is actually very coupled together, so that means we do need a lexer, right? So okay, so let's include the lexer as well, why not? I mean, in the final compilation, the stuff that is not used is not going to be included into the final program anyway, so whatever. Right, so this is going to be lex.porth, right? So we're including all of that in here, and unknown word silent. Oh, okay, so this is one of the options of the compiler. So in the option of the compiler, we have a global variable, global Boolean variable that basically suppresses any like auxiliary logging of the compiler, right? So when it's a global one, so this is something that you may want to control or may not want to control, right? So we're going to include that here as well. Right, so let me see if we have anything else. There we go. So we have some stuff in here, right? So it actually takes some time to like compile it properly, but apart from that, it seems to be working. What's funny is that the size of the final assembly file, is like brain.asm, is not that big, right? So that's the size of the whole thing. Even though we included so much, look how much assembly we generated anyway. This is actually pretty cool, right? Look at that. So we included so much shit. in here, right? Basically, like the majority of the compiler is included in here, but here we have only that, and this is because we eliminated all of the dead code, right? Whatever we don't use in the compiler is not going to be included in the final executable anyway, so I don't really worry about including too much. Zero cost abstractions, by the way, right? Zero cost abstractions, right? Let's actually get used to, you know, promoting our language with propaganda and stuff like that, because otherwise you won't be able to promote your language. All right. So in the compiler, we have essentially a global array of opcodes, right? So it's a global array of opcodes, and you can push things into these like array of opcodes by doing push op, right? So, and what we need to do, we just need to basically go through the Brainf source code and just push the intermediate representation operation. So maybe we want to start with reading a file, right? So I think it makes a lot of sense. So let's actually do the following thing. Let's implement the usage command, which accepts the name of the program, right? Accepts the name of the program, and probably also it should accept, I don't know, the file descriptor where exactly we're going to print the usage, right? Right, so where exactly we're going to print all of that. So this is going to be program, and this is going to be fd. And in here, what we're going to print is essentially program sister to str. I might as well actually print it like this, maybe. So this is going to be usage program. Then we'll have to print it puts. This one is kind of tricky, right? So this has to be fputs, fd fputs, and then what do we want to have in here? I suppose we want to have main bf, right? So some sort of like input bf, and then a new line fd fputs. Do we want to have anything else? Do we want to have anything else? I don't think so, right? So that's the main usage. We're not going to add any flags yet. I think we're not going to add anything, so that should be fine, hopefully. So that should be fine. Let me see. So we're also going to have, you know, argv stuff. So how do I want to save all of that? I want to just basically... I need an easy way to control all of this. So maybe I'm going to have like a memory args, which is the size of a pointer, so I can take the argv and save all of that in here, so I can just like increment this entire stuff, right? So then I can have a program, which is the size of the pointer. I don't know what's going on with Emacs, then argv pointer, dereference it several times, and then program, and just save it as a pointer, right? So then I may want to actually steal some of that code from existing port program. Let me actually see. So where is the args? Here is the args. Yeah, so this is literally what I do in here. And every time I need to increment, I actually increment this thing like that, which kind of makes sense. Sure. Right. So let's go like this. And if argv pointer is null, that means the user has not provided any of the input file, right? So we'll have to throw some sort of error. Error, no input file is provided, right? So this is the error, and we're gonna exit with non-zero exit code. On top of that, we may want to print the usage, so we'll have to do program std error usage. There we go. Right, otherwise we're gonna try to do something like this. Right, we're gonna say compiling puts, then sister to str puts, then a new line puts, and we're gonna align this entire stuff like this. Right. So, and let's just like try to compile. Compile an error. Nice. Okay, that's really strange. Why did it print that in that specific... Oh, okay, I see. So it was terminated by... so it was basically, you know, seg fault, right? It was basically a seg fault. That's why you have to program in Rust, in a memory safe language, right? Where you can have memory safe buffer overflows. So so it means, oh, I couldn't argue it, like I couldn't actually like get like that. Okay, so no input file was provided, as you can see. So right, basically we already have an executable brain, by the way. Right, so here's the executable brain, and then we can do something like hello bf, and it will say compiling hello bf, but obviously hello bf does not exist, so we'll have to create one. I'm gonna just steal some stuff from the internet, right? And let's go. So we're gonna use the classical hello world, right? Let me actually find a classical. Is there like a, yeah, I want you to see like a compressed one. Hello bf, right? So here is the hello bf. So the first thing we probably want to do, we want to open the file, right? So we want to open the file and like read it. So luckily we have a pretty cool function called map file, right? Excuse me. We can just literally do something like this, and that gives us the contents of the file as a string, and we can like instantly print it, right? So which is rather convenient. So let me actually do something like this. I'm gonna compile the brain.porth, and what's cool is that I can instantaneously try to compile the hello bf, right? There we go. So as you can see, we printed the contents of that file, so we can already iterate through the source code and start doing things, right? So let's go ahead and do that. Let's go ahead and do that. While so the string actually has integer and a pointer, right? So if you take a look at the current stack, right, there's nothing on the current stack because I actually printed it. So on the current stack, currently you have a pointer and you have an integer, all introduced by map file, right? So an integer is the size of the string, and a pointer points at the beginning of that string. So what we need to do in here, we need to do while, peek into that n, right, and see if it is empty or not, right? So while it is not empty, while it's greater than 0, we're going to continue like doing the loop. Right, and in here, we're gonna just grab this entire stuff and basically switch upon different characters we encounter, right? So let's actually take a look. So this is the character, and if the character is equal to plus, we have to do one thing. If it's equal to minus, another thing, and so on and so forth. So I suppose I'm gonna just like stub all of that. So S8 minus. What else do we have? What are the commands in Brainfuck we have? What are the commands? So plus, minus, dot, comma, right, dot, comma, so it's more of a like right, left, and the most interesting one is basically while loop, right? So it is basically while loop, else. I could have actually done it like that, so it's going to be something like this, and the second one is going to be something like this. Otherwise, we have like a lot of freedom what to do otherwise. I suppose if we encounter something unknown, we can just ignore like unknown characters, like maybe spaces, right? So you may want to like indent things to look good, and because of that we may want to ignore the spaces, right? So I'm going to just put end in here. Okay. So let's do the following thing to do. Plus is not implemented yet, right? So another one. Minus is not implemented yet, right? So can you do something like this? Right? Oh shit! I should have actually done it like that. Maybe I could have. Make it more simple. Alright, so this is not implemented yet, then this is not implemented yet, to do this is not implemented yet, and to do this is not implemented yet. There we go. So that's cool. We might as well maybe even report sort of like where we are right now, but maybe not. Hey Zozy, do you get enough sleep? I'm literally neat. Of course I get enough sleep. I can get enough sleep at any point. Like, I mean, I'm neat. So I forgot what it actually stands for, like precisely. Right. Not, yeah, not in education, employment, or training. Like of course I get enough sleep. My schedule might be fucked up, but I do get enough sleep. So, anyway, all right. So, all right. How are we gonna do all of that? So, I think we need to prepare the head, right? If that makes any sense. So essentially, we're going to utilize this stack of porth, and we're gonna only use one element on the stack of abstract porth machine, right? So only one element on that stack, and we're gonna use that element to point at the beginning of the memory of Brainfog, right? But that also means that we have to initialize that memory. Oh, also, by the way, I just realized that the porth compiler expects you to have a main function, right? So it expects you to have a main function, so which might not be super easy to implement, but it shouldn't be that hard if you think about it. Right, okay, so let's actually start with defining a function. Right, so I need to find the compiler, right? So this is gonna be com push op, right? So we need to push the type. The type of the operation is gonna be op prepare procedure. So I'm preparing the main procedure. So I do not remember what the operand of this thing stands for. So we'll need to actually take a look at that. Prep proc, right? So I have documentation. Prep proc. The amount of bytes of local memory to allocate on the stack. Oh, that's actually pretty cool. So basically, when you enter the procedure, like the porth will allocate certain amount of bytes for the local memory. Since we don't need any local memory in here, so I think I'm gonna put 0, right? So I think that makes sense. Right, push op, and the token. Okay, this one is rather interesting. So token is basically where it was introduced, and it is needed for reporting the excuse me, reporting the errors and stuff like that. So I'm not really sure. So we can provide we can just provide some sort of like an empty token, right? So empty token, right? It doesn't really mean anything. So as you can see here, like, we are not using the compiler by its like intended way, and that's why this like doesn't really fit here really well, right? So we don't have a notion of a token per se. We may introduce a notion of token, but tokens from porth do not necessarily fit in there. So yeah, it's kind of strange. Okay, so this is a push OP. So, and I probably need to allocate that thing somewhere. So it's going to be memory, empty token, size of token, right? So this is the size of token, size of token, memset drop, right? Memset drop. After that, we can just start introducing things. Maybe, right? I suppose we'll need to push the pointer to the beginning of like certain memory. So we probably also need to define a memory, right? So if I take a look at the compiler, define memory, or maybe it's called memory define. So we have global memory define, right? So it accepts, if I understand correctly, the memory structure, size of memory, right? So it accepts the name of the memory, right? The offset within the memory. And the location where it was defined, which is rather strange, right? So offset within the memory. Offset within the memory. Ah, I see what's going on in here. Okay. So that is actually defined by a variable, global variable called global memory capacity. So if we want to, like, have a certain amount of global memory, we can just set that global variable like that. So how much memory are we going to have in there? So let's put it something like bf memcap, right? And I'm gonna just save it in here, and we'll have to define that thing somewhere. So it's gonna be proc main const, and let's say we're gonna have, like, you know, 1024, right? 1024, and that should be enough, I think, right? So we have a global memory capacity, then that, and this variable is used in the code generation, right? So it's used in the code generation, right? So to generate the code accordingly. Okay, that's pretty cool. So then we start the procedure. After that, we need to push, right? Push a pointer, right? So we're pushing a pointer, and the value of that pointer, actually, this is not a push a pointer. I think it's a push global mem, and by pushing global mem, you specify the offset. So that means to refer to the beginning of the memory, we can quite easily just put 0 in here, right? Because it's offset from starting, like, of global memory. So we don't even have to do anything about that. That's actually super cool. So that's a very convenient intermediate representation, right? Push a pointer to global memory, so the offset from the start of the uninitialized global memory region. Right, so we're gonna have something like this, empty token, push OP, right, so there we go. So this is the first thing we do in here. Cool. So when we encounter plus, right, when we encounter plus, what do we want to do in here? We essentially want to duplicate whatever we have on top of this, like, yeah, we essentially want to first read the value from this specific pointer, right? So we want to read the value from this specific pointer. So what I need to do OP intrinsic, right, intrinsic. Then I'm going to say intrinsic, and intrinsic is going to be dupe, right? This is dupe, and then just push OP. So basically, I'm programming in Porth using Porth intermediate representation. Yes, that's what I'm doing. Like, I'm programming in Porth, but using its intermediate representation, like just pushing these like instructions and stuff like that, which is actually kind of cool. All right, so the next thing I need to do, I need to basically load. I think I have to say load 8, right? So was it load 8? I don't remember. At OP load, I'm gonna go in here, OP. Oh, I think it was also intrinsic. Intrinsic load. Yeah, it's also intrinsic. Okay. Intrinsic load 8. Right. So there we go. Essentially, we have now value in there. Then I want to do OP push integer, right? And I'm pushing 1 in there, right? So there we go. And then I do OP intrinsic like this, and then I do intrinsic plus, right? So intrinsic plus, and I just save it like this. Okay. So, and now I have to save it back, right? So I need to do intrinsic essentially over, right? So to copy a thing over there, and then I need to do store 8. So that should be basically it, right? So that should be basically it. There we go. So this is implementation of the plus, right? So if I have the head of the brainfuck at the top of the stack, right? So this is the head. I duplicate the head, I dereference it, 1 plus 1, then I copy head over here, then do a store, and I have a head yet again in here, so that should be fine. Okay, so I can now remove that. Minus is super easy, right? Because you can just do minus. Right, so this is gonna be minus. Okay, that's cool. So we already have plus and minus, theoretically. So we may want to just ignore the rest of these things for now, right? And just implement the generation. But before we implement the generation, we need to close the procedure, right? So here we started the procedure. Here we generated instructions for the procedure. And now we have to return from the procedure, right? So, and the procedure has to be like something like ret. And that is also not enough. We need to define that procedure. We need to let the Porth backend know that such procedure exists, where it starts, and so on and so forth. Right, and we also need to say that this procedure is called main, because this is how Porth backend knows where to start executing the program. So yeah, now let me actually do the following thing. So let me find the like proc define or something. Yeah, so size of proc. So we need to oh my god, that's actually a lot of things in here. But it should be fine, I suppose. Right, so it should be fine. Okay, so majority of the things are not really that important. We need name, the address where this entire thing starts. The location is where it's defined. Ins, outs are needed for the type checking. Then inlineable is needed for like inlining and stuff like that. Size, I don't remember what size is used for. I think it's also used for. I think it's used for type checking the inlined procedure. Right. So when you inline the procedure, we use the size to know how much we have to skip to continue type checking. So majority of these things are not needed. We only need name and address. So that should be fine. All right, so let me just do the following thing. Okay, so this is going to be brain.porth. So this is going to be memory proc. Size of proc, and I probably also want to do something like size of proc 0 mem set drop, and right, so probably have to set something like proc in here. So the address is already 0, right, because we start at 0, right? So we start at 0, we don't have to do anything in here. The only thing we need to do is just set the name of the procedure, right? So it's going to be proc name pointer plus, and then we have to say that this is the main, and we'll have to save it in here. Right, there we go. So after that, I think we finished defining the main procedure, and we can just go ahead and generate this entire stuff. Right, so we can say that like generate output. Though we can use the name, right, we can use the name to do that, I think. Right, so essentially what I can do is I can do tmp end. This is where the buffer starts. Then I'm gonna do this thing, then I remove extension, right, so I can just remove the entire extension, and I'll need to append that to the temporary buffer, right, so I just appended it in there. Then I'm gonna append asm, tmp append drop, and then I need to finish that with the null terminator. So the easiest way to do that is just to do something like this. Tmp append. So essentially tmp append accepts two arguments, the size of the buffer and the buffer itself. So I can use the null terminated strings as the buffer, as the source of null. Right, and then I can say that the size of that buffer is 1, and it will literally copy 0 from that string literal. So that's basically how I did that. Right, so it's a weird hack, but it works. Right, and then I can just like take that and generate like asm out of that. So it says yasm, let's actually do fuzm, right? So that should generate the, you know, the thing. So we can also log that. We can say something like info, right, so it's going to be puts. Then I can duplicate this entire thing, convert it to a sister, and puts it again. Maybe I'm going to say generating this thing, and then we're going to put like puts one more time. We're going to align it like that, and there we go. So this is a little bit of a logging. So here we prepare the file name, then we log that file name, and then we're actually using it to generate, you know, that file specifically. Okay, so let me now try to do that. Okay, so it didn't work because I forgot to do empty token in here. There we go. Compilation. Okay, so argument push OP. Oh, you have to provide the, I forgot that I have to provide the empty token. Empty token. So then it's gonna be empty token. All right, so remove extension is expected in but cut integer. This is interesting. This is because remove ext expects the sized string, so we have to convert the sister to str. Right, and I think that should be the last error, hopefully. No, it is not. Okay, so insufficient data on the stack. Oh, I see. So we consumed n and s, but we didn't put them back. So what we have to do is just like, we have to put them back, decrement the size, and increment the pointer. Right, so we shrink the string that we are consuming. Right, and then generate FASM Linux. So I'm really surprised. So we have unhandled data. So where is that unhandled data coming from? Oh, okay. So at the end of this loop, we also want to drop that entire data. Right, there we go. Okay, so that's pretty cool. Look at that. So it complained about this thing being not implemented, right? So maybe we want to have an example that only have plus and minus. Let's have something like simple BF, and it literally has plus and minus, right? Let's try to compile plus and minus and see what's gonna happen. Right, so simple, and it did something. Type checking phase did not check the existence of main procedure. Ooh, yikes. That's actually pretty cool that I actually implemented that. This is why I put so many assertions. Even though, like, yeah, it should just work. Well, you never know how exactly your code is going to be used. Now I'm using my code of the compiler outside of the context of the compiler to compile a completely different language, and assertions are breaking. Right, all the assumptions the compiler used to make, they are completely wrong. So it's very important to just like, you know, state those assumptions, assert these assumptions. And even though I defined the main procedure, I never actually registered it. Right, so I should have actually registered it. So as far as I know, I had to do define proc, right, or proc define. Proc define, yeah. So I have to do proc define. So yeah, I have a structure, I define it, and now I have to just like do it like that. All right, hopefully that should work now. And okay, so that's actually very funny. So the first generating simple ASM was, why did I print it twice? Oh, I know why I printed twice. Because generate FASM already prints that for you. You don't have to do that. Okay, the compiler actually logs that shit for you. All right, let's take a look at simple ASM. So this is a compiled version of this program. This is assembly of this program. Right, and of course it includes implementation of the print intrinsic, because we're reusing port compiler for that. Okay, we can't see shit in this mist, by the way, because we don't have any annotation. Right, so I probably want to do the following thing. I want to bring the annotations back. So let me see. I think I remember like having a to-do in there. Right, so introduce flag to, yeah. So maybe I'm gonna have like a global. Let's actually introduce like a global variable. I think it's a good idea. So in port.porth, we already have silent, right? And we may introduce like annotate, right? Size of boolean, right? So annotate, and if annotate is true, just do that, right? Just do that. Brainporth, and of course in here we're gonna have annotate. And I'm gonna say, please go ahead and annotate. Right, so this is gonna be Boolean. Oh, right, so what do we have in here? And if I open simple asm now, we have all of the annotations. Look at that. So this is where, yeah, so all of the locations are broken, but this is something that we may potentially fix. What's interesting is that, do we really need... Yeah, we do. Okay. Yeah, I don't know. Do we really need the token? Because there is always a token associated with OP. I was thinking, can we just store the location instead of the token? Right, but I don't think we can, right? Because the token is needed for some of the names we use in there, so it's not going to be the case. Anyway, in any case, so here's the stat, then we have the global memory, then dupes and reads and stuff like that. So as you can see, it is working. We can try to run this program, even though it's not going to do anything interesting, right? Oh, okay, so this one is interesting. We didn't even compile that program. So our compiler doesn't really do anything. Oh, okay, I'm sorry. Oh shit. Yeah. I thought some toxic people came in and started to call people names or something like that. Because I didn't see the full context in the chat, and it just like sometimes look weird. I'm sorry. So we have a subscription, and int82, thank you so much for 5 months of tier 1 subscription. Thank you. Okay, so it doesn't really do anything interesting, so I suppose it makes sense to just continue working on it. But what I want to do, I want to make this thing like at least compile some stuff, like at least, you know, call FASM. So I'm gonna just copy paste some code from Porth, right? So let's just go ahead and copy paste some code from Porth. So what we're gonna be probably using FASM. So yeah, okay, so that's fine. And here we are. I don't really know. Well, yeah, I think I'm gonna be using FASM, that's for sure. Might as well include the timing. If I'm gonna be just copy pasting this code, that means I'll have to also introduce the oh boy, the base name stuff, right? So it has a base name thingy, which is fine, I guess. Right, yeah, so I'll have to introduce base name. And the base name is essentially like a regular name, but just stripped off of the extension, right? So essentially I would use something like base name, base file path. Did my keyboard just died? My keyboard just died, what the fuck? Okay, just a second. It just does it from time to time. Okay. Base file path align TMP. Alright, so base file path, and this is gonna be awesome. So that means I'll have to prepare it, unfortunately. Okay, so let's do something like memory, base file path, size of str, and that's essentially just taking this thing, converting it to sister to str, and then removing the extension, right? Just removing the extension, base file path, then str, right? Base file path and then str. Let's try to compile. So it's probably gonna complain. Yeah. That's why I implemented static typing. Okay. Oh yeah, I do remember. So there's also one thing that you have to do after you generated all of the instructions. You have to mark up OP labels, right. So since I removed some of the unnecessary labels, I just by default don't generate any labels for anything, and I have to run a special procedure that goes through all of the OPs and just figures out what needs to be marked and what needs to be like labeled and stuff like that. So yeah, after we finish generating everything, what we're gonna be doing is like markup OP labels. So that's important, and that didn't help. Very cool. So I don't know why. Let's take a look at the simple ASM, right? So let's take a look at the simple ASM, and yeah, it didn't generate shit. I wonder why, right? So because it should have generated like OP, like a label at least for prep proc, right? It should have done it at least for that. Markup OP labels, right? So if it is proc, it should have actually set this thing to true. Right, and when we generating everything, it should have like done that, but I really don't know why it didn't work. Oh boy. So. I kind of want to dump this stuff that I got. In the compiler, if I remember correctly, I have a function that allows me to dump stuff. Right, so it's basically dump ops. Right, and where is it implemented? I hope it is implemented in the compiler, right? So, and this is probably where I want to do that. Let's do dump ops and just exit in here. Right, so this is what we've got. These are the ops. But do they have like a label or not? Right. So we may want to introduce that additional information in the dump ops, right? Dump ops. In the dump ops. Okay, so essentially, oh, that's a lot. Dupe OP token, actually OP label, pointer plus, and it's a boolean. And if it's true, I don't know, we can do something like. Yeah. So this is puts, otherwise it's gonna be like that. So it is in fact marked. It is in fact marked as to have a label, right? It is marked to have a label. Okay, that's cool. Then, if I go back to brain.porth, let me just regenerate everything, because I'm not sure what is going on. Oh! Of course! I'm generating assembly after I'm running FASM. Of course it's not gonna work. I wonder why nobody told me that. Alright, so that explains everything. Okay, so it's just like, alright. Alright. Okay, and as you can see, it compiles now. Right, it just perfectly compiles. So now, right, we have a simple thing which we can just run, and it doesn't do anything, but at least it exits with, you know, successful code. So, what do we have in the chat? Some spammers. Ban, ban, ban. All of the spammers are banned. Okay, so thank you so much, Salary Bot, for 5 months of tier 1 subscription. Hope you're feeling better. Getting brain fogged is probably not helping though. No, it's fine. I do feel better. Thank you so much for 5 months of tier 1 subscription. Thank you, thank you, thank you. Spoomers. Spoomers are banned. What's up, Nothing? You were asking why compiling is slow for brain.porth. Where? I don't remember asking that, and I don't remember ever caring? What? Okay, whatever. Chat is just being chat. I don't know why I'm reading the chat, so I just like continue working. Okay, so well, I mean, I still need to read the chat because I need to moderate it, because every time like I distract, people start spamming shit. Anyway, so what do we have? We need to continue implementing this entire stuff, right? So let me see. So it's gonna be brain.porth. And so what are the other instructions that we need to implement in here? This one is rather interesting. Okay. Okay. Ooh. I remember dot. Is dot, it's a put character. Okay. So what we need to do in here is we need to duplicate and read whatever we have. Not really, actually. I think it is enough to just duplicate it. Right, so essentially we have the head, right, and we just duplicated it. But that's not enough. We may want to put op push integer 1 empty token push op, right. So we push 1, and then instead of duplicating, we're going to do over. So here we have one head, which is a perfect amount of arguments for a write intrinsic. So now we can do something like op push int std out, right? So which is constant, which is literally a constant, right? So something like this, and empty token push op, and then I can do op intrinsic syscall 3 empty token push op. Okay, so but this is not enough. We also need to push the code of the syscall that we're trying to call. So it's going to be push int sys write empty token push op. Okay, so this is actually pretty cool. Look at that. Yeah, that makes a lot of sense. So basically I'm using the pointer as like pointer to the beginning of the buffer, and I'm just printing the buffer, and I say that the size of that buffer is 1 character. So that's what I'm saying. So which means I should be able to write a very simple program called E, right? So imagine that you have 69 pluses. There we go. You have 69 pluses and you print 69 pluses, right? So you're basically going to print the character with the ASCII code 69, which is capital E, if I remember correctly, I think. Right, so this program should just print E on the standard output, hopefully. Okay, so let me recompile the this stuff, and I'm gonna just like do it like that. Okay, couldn't open file ebf. I call it porth for whatever reason. eporth. Okay. ebf. All right. So yeah, now we have easm, right? So easm. That's pretty cool. And I can quite easily try to run this entire thing. And it prints E. So yeah. So this is the source code. This is a native executable that we generated from that source code. And if you try to run this native executable, it prints E. We have a working native compiler for Brainfuck. You could call this sort of BF Porth transpiler. Well, okay, and if you're using LLVM, you're just writing a transpiler to LLVM bytecode. Every time you use an LLVM, you're not writing your own compiler. No. You're just writing a transpiler to LLVM bytecode. So if you want to go that route of, you know, of minifying things, you can't use LLVM. You just like are using like making glorified preprocess for LLVM. So yeah. Anyway, so let me see. So we can do the same thing for a read, for example, right? So it's going to be literally the same, actually. Right, so it's going to be that, but instead we're going to do std_in, and we're going to just use read. So we're going to be literally reading into the memory, right? So we... Oh, by the way, there's like a very important thing. We need to do op intrinsic, intrinsic drop. Empty token push op, right? Okay, so what's interesting is that I'm not generating the source code of Porth. I'm not generating the, like, I don't know why it is not clear for people. I'm not generating the source code of Porth. I'm generating intermediate representation that is used also by a Porth compiler. Intermediate representation not equals to the source code. Okay. So, cool. And it's also super... Okay, I'm not going to read the chat again. It's also super easy to implement like left and right and some other stuff. Right, so what we have to do in here, so here's the head. What I have to do is just like push integer, op, push integer 1, empty token, push op, right, then op intrinsic, intrinsic, and then it's going to be op intrinsic plus empty token push op. So, and that should be it actually, I think. Right, if it's going to the right and if it's going to the left, it's going to be minus. Right, cool. So we implemented all of the like non-control flow related things, I think. Right, all of the non-control flow related things. Now we need to implement the actual control flow, and it's going to be very interesting. So essentially, yeah, we'll just we'll have to pull off the loop thingy. And the question is, how we're going to be doing all that? We'll probably have to use the control flow stack. Right. So, okay. So when we're starting, when we're opening this thing, I think we'll need to push op while 0 empty token, push op. But on top of that, we'll have to use the control flow stack. And the control flow stack is available in the compiler of Porth, right? So it's going to be com Porth control stack. I forgot what is it called? Proc compile file. So yeah, parse block stack. Yeah. So it's a parse block stack, and it essentially allows you to push integers and pop integers. It doesn't really do anything particularly special, right? But you can use it to, for instance, remember the position of while, right? So that's one of the things you can do. You can remember the position of while. Okay. Though, do we really need to remember position of while? We probably do need to remember the position. Okay, so I'm gonna do it like this. So I have to put an integer, and do we have a current IP? So there was a procedure. Our current IP is just basically the amount of operations that we have, right? So here is the current OP, right? And I put while in there, cool. And then I'll need to implement a bunch of operations, right? So I need to check, right, whatever value in there is equal to 0 or not, right? So yeah, while it is not equal to 0, which is nice. Okay. So OP. So I probably need to duplicate whatever we have on top of the stack, right? So let's duplicate, and let's also load it up. Duplicate it and load it up. And the question is equal 0 or not equal 0, right? Might as well just push OP, push integer, empty token, push OP, right? Okay. So, and OP intrinsic equal, do I have not equal? No. Or do I? I think I saw something like NE. Not equal. I think NE stands for not equal. Right, so while it's not equal to that stuff, push OP. Right. And after that, I need to put the do instruction. But before I can put a do instruction, I need to save the current location in the control flow stack. So I'll have to do OP in OP do. Right. So I need to remember. I think I can just put 0 in here, and this one is empty token. Push OP. There we go. So that should be the implementation of the open bracket, right? So essentially we just like prepare the while loop, right? And we're gonna close that while loop in here. We're gonna pop all of these things from the control flow stack, and we know the corresponding locations of do and while, and we can prepare them correspondingly, right? So that's basically what we can do, essentially. Okay, so and in here, what we are doing, right? We are popping this stuff. So this is going to be that. So this is pop, and we have to do that twice, right? So and in here, so if I pop this thing first, I'm gonna have do IP, right? And I'm gonna the second one is gonna be while IP, right? So when I close the loop, I know the addresses of the corresponding do and while, so I can adjust their jumps accordingly, so to speak. If that makes any sense, right? So that's what I can do. As far as I know, while doesn't really need to be updated anyhow, right? Right. So you can just keep while. But do requires to jump after after the end while block, right? So we have a special end while block. We can even do something like this. So op count, ops count. Right, so in here we're gonna have basically end IP, right? So this is the end IP, right? And I might as well do something like I don't know. Yeah. So because all of these things are relative and my brain is slowly like kind of fading away, but I'm almost there, so I don't want to give up right now. So yeah, maybe I should make a small break. Yeah, I should make a small break. So I could force myself because it's almost like a finish line, but I don't want to do that, especially because I'm sick. So I'm gonna make a small break, and after the break, we're gonna finish the while loops, right? So yeah, let's make a small break. All right, so let's continue implementing stuff. Rate, and let me actually see the definition of the of all of these, not intrinsic but operations, right? So let's do something like that. OP do, right? So the address of set to jump by forward when the consumed value is false. Right, when the consumed value is false, but if it's true, it's gonna actually fall through. Right, so that thing must be equal to the distance. Yeah, it must be equal to the distance between the current thing, and the current thing is essentially counts, right? So I read it like that. And the like do IP itself, so we actually find the difference between them. Right, so here is the difference between them, and that's how many steps I have to jump. But I have to actually jump over the end, so I have to add 1. Right, and this is where I have to save that into the OP of do. Right, so maybe it would also make sense for me to like create the following thing. So do IP size of OP multiply and then ops plus pointer, and do the same thing for the while IP, and just have something like do OP and while OP. It's not the previous code, but I mean, I just don't care, right? I just need something to work with. Might as well collapse these two lets together, believe it or not. I think it is possible to collapse them. So essentially I will move these two things here, and in here I'll just do over, and there you go. So now I have do IP, while IP, do OP, and while OP. So as you can see here, I can combine the force style and the port style of like manipulating the stack, and it's actually quite convenient. Right, so now I have all of the necessary information. I have their specific IPs, their specific indices, and also their specific pointers. It's quite convenient, I think. Alright, so for the do OP, I have to do OP operand, right? An operand is basically an N of set, right? So, right, and then I just save this as an integer. So this is for the do. This is for the do. For the end, it's going to be slightly more interesting. I think we also need to probably take this stuff, right, and then do while IP, right, while IP, and subtract that. So this is N of set, but this is N of set to jump backwards. So it's also fine. But we'll have to do that somewhere here probably. So. And I suppose it's going to be OP and while, right? So this is OP and while, empty token, and just push OP. And that is basically it. I think that is basically it. That should be basically it. Okay, so then I mark up the labels and then prepare the procedure and stuff like that. So the next thing I want to do, I want to dump the operations and exit. Don't generate anything. I just want to take a look at the generated operations, right? So let me compile everything. Yeah, so pointer plus. It's supposed to be pointer plus. Argument integer, so it has to be something like this. Okay, that's cool. So this is what we've got. It's just E. Okay, let's take a look at hello, right? So hello BF, and this is basically like while loop and whatnot. In fact, I want something simple. Let's actually go to simple BF, and I'm gonna just do something like that. I just want to see if it handles the loops correctly, right? Does it handle the loops correctly? Simple BF, show me the intermediate representation, right? No, it even marked up everything correctly. That's actually very cool. So I don't remember what while is needed for. I think while contains this size of the entire like loop section, so you can quite easily, you know, skip it during like type checking. But we changed type checking; it's not really needed anymore, so it's kind of whatever. Right, so this OP do jumps by 8 things forward. 1, 2, 3, 4, 5, 6, 7, 8, and it jumps over the while. This one jumps backward by 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and it jumps right back into the while. And as you can see, while is marked as to have a label, right? So okay, so everything looks all right. So this should be a proper program, if I understand correctly, right? Okay, we can now take a look at the hello example. So here is the hello example. It's a little bit more complicated, right? And it should have like several nested while loops. So let me take a look at, for instance, and while, right? So it actually jumps like by 100 operations and whatnot. Okay. After like everything, I think it makes sense to maybe assert that we don't have anything in the parse blocks, but maybe not, whatever. Okay, so now we can try to generate the actual program, right? So the actual native program. So this is going to be hello BF, and we should have the hello executable. So here is the hello assembly, right? So this is the assembly that we generated. This is the assembly that we generated from the hello BF, right, from this thing. And then we compiled it down to hello executable, which is static executable, statically linked executable. And if I try to run hello now, it says hello world. We natively compiled to native instructions a Brainf program using the backend of our compiler. What is the difference between intrinsics and operands? Basically, an operand can be a specific operation. So any intrinsic is an operands is not really. You probably mean operation, right? So what's the difference between intrinsic and OP, right? So any intrinsic is an OP, but not any OP is an intrinsic. That's basically what it is. You know what's cool? You know what's cool? Actually, I wanna kind of get rid of the annotation. So let me quickly do that. I'm gonna show you something very, very cool. Alright, so we don't have an annotate, and I'm just gonna yoink it back. So nothing is annotated. Where's brain? So this thing is absolutely self-contained. In fact, I can literally give you this assembly and you're going to have the Brainfuck compiler working on your machine, working on your Linux machine. So, and this is precisely what I can do. So I'm gonna take the assembly of this Brainfuck compiler and release it under MIT. And I'm gonna just upload it to GitHub for anyone to verify that it actually works. Right, so this is gonna be something like this. And the instructions on how to build this entire thing. So maybe we're gonna, yeah. So the way you build the thing is the following. Brain awesome. Right. And then you do brain. Yeah, you just call it. Right. So you'll need FASM. And let's actually go ahead and do something like this. Porth demos. Technical demos from Porth streams. So I'm gonna have a look. One more time, because I lost it. Didn't I not do that? I think I'm an idiot. Okay. And Porth beta brain. Cool. So we might as well also just take hello world from the Wikipedia. Hello. All right, and you can try to go ahead and verify that this entire thing works. Yep. So this is the entire compiler. And since it's statically linked, right, it doesn't really care what libc you have on your distro. So theoretically, it will work on any Linux distro. Theoretically, like any Linux distro that has more or less a recent kernel, right? So yeah. Add the brain demo. Right, and I'm gonna just push that right into the repo. So yeah, there we go. So here is the Brainfuck compiler using the Porth backend, right, under MIT license, but it's assembly. So yeah, I'm gonna open all of the Porth code that I wrote recently. Right, that I wrote recently, later when I'm done with the design of the language, right? So try it on your computer, by the way. Try it on your computer. Does it work on your computer? Because theoretically it should work, right? So, but you never know. You never know, actually. So, yep. Does anyone have any questions, maybe? And of course, I'm going to put that in the description for anyone who's watching on YouTube. Oh boy, where is my description? There's so many. Okay. Porth demos. All right, I guess there's no question anymore. Thanks everyone who's watching me right now. I really appreciate that. Have a good one, and I see you on the next session. So yeah, thanks everyone for watching. Love you.